right, so we're going to be analyzing more arguments using the same method of truth tables. So here's our next one. The first premise, I will go out for lunch or I will make my own lunch. Second premise, I did not go out for lunch. Conclusion, I made my own lunch. So this is the first example that we've looked at where the first premise is not a conditional. All of the previous examples we started with a conditional, but there's no if-then here. There is, however, the word or. So instead of a conditional, we have a disjunction here. So let's think of what our component statements would be. Remember, a disjunction is something of the form P or Q. So it makes sense that P would be, I will go out for lunch. Q, I will make my own lunch. Okay, now let's reduce this down to symbolic form. So I will go out for lunch or I will make my own lunch. P or Q. P or Q. I did not go out for lunch. Did not. This is a negation. And specifically, it's the negation of P. I will not go. I will go out for lunch. So we have not P here. The conclusion, I made my own lunch, which is what Q is saying. Okay? So we have our symbolic form, two premises and a conclusion. Let's put this in the form of a compound statement that we want to analyze. P or Q is my first premise. Not P is my second premise. We form a conjunction out of those. Implies my conclusion, Q. Okay? Let's form our truth table now. So we're going to have, once again, two component statements, P and Q. And this time I'm not going to forget to do my negations first. So I am looking for negations and I see 1, not P. Okay? I also have a P or Q in these innermost parentheses. So let's start there, P or Q. Then I can take both of these, put them together into a conjunction. P or Q and not P. Finally, that entire thing is the antecedent in this overall conditional here. So I can finish this off with the entire statement. P or Q and not P imply Q. Let's get some columns. Here we go. All right, first two columns are always the same. True, 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 false, false, true, false, false. Next up, I have a not P. So take the opposite of these truth values here. False, false, true, true. Now we have a disjunction, P or Q. Remember, these are going to be true anytime at least one of your truth values in these component statements are true. And if you notice, in the first 3 rows, I have a true showing up somewhere. So true, true, true. In the last row, I have a false in both positions, so that's going to give me a false there. All right. Now, I have a conjunction with the previous 2 columns, P or Q, that's here, not P, that's here. Conjunctions require both statements to be true in order to be true. That only happens in the 3rd row. So I have true there, false everywhere else. Okay? Now, take this column as my antecedent, Q as my consequent. The antecedent is false in 3 cases, and we know that that forms, or that gives us a truth value of true in all of those cases. And then here I have true implies true. The conditional will also be true in that case. Notice it's a tautology, so that means that we have a valid argument. Okay? So again, this was the argument form. P or Q, not P, implies Q. So those are my premises. Q is my conclusion. Any argument that takes that form is always valid based on what we showed here. And those types of arguments are called disjunctive syllogisms, or sometimes we call it the law of disjunctive syllogism. Interesting name, and it's just what we call that form. So there's another one for the toolkit. I have one more argument that I want to analyze before we wrap up this section and this chapter. This one's a little bit more involved. There's going to be actually 3 component statements as opposed to just 2. So our truth table is going to be much larger. Okay. If I major in engineering, then I will take Math 400. That's my first premise. If I take Math 400, then I will take Math 401. Second premise. Conclusion. If I major in engineering, then I will take Math 401. Notice that both premises and my conclusion are all in the form of a conditional. So starting with this first conditional, we should have an if P then Q that we can identify. P, if I major in engineering. I major in engineering. Which, by the way, you can't major in engineering. You have to major in something more specific. Civil engineering, mechanical engineering. But it's just for the sake of this argument. Q. So if this is if P then Q, Q is I will take Math 400. That's Calculus 1. Okay, notice the second premise. If I take Math 400, well, we already have I will take Math 400 as the statement Q. So we don't need a new letter for that. Then I will take Math 401. I will take Math 401 doesn't show up in either of these. So that's going to be what I call R. I will take Math 401. All right, so let's put this in symbolic form now. The first statement, if I major in engineering, then I will take Math 400, is P implies Q. Okay. Next statement, if I major in Math 400, then I will take Math 401. Q implies R. Final statement, or the conclusion, if I major in engineering, that's P, then I will take Math 401, that's R. So the conclusion is P implies R. Okay, and again, this is the type of argument that you might be able to look at and reason out in an informal way. A lot of arguments you can do that. But we want to see what the formal approach gives us. So now I'm seeing that we have 3 component statements, which means my truth table is going to have 8 rows in it. And I need a column for P. I'm sorry, actually, let me get my, before I create the truth table, I need to create my compound statement. So we have P implies Q as our first premise. Form a conjunction with that in the second premise. Q implies R. That becomes the antecedent in this conditional, where the consequent is P implies R. And you notice there's just arrows everywhere in this compound statement. Okay, now let's look at our truth table. So I need 3 columns for my P, Q, and R. Then I have conditionals. P implies Q. Q implies R. Those 2 conditionals, I'm forming a conjunction out of those. P implies Q, and Q implies R. And then finally, this entire conjunction is the antecedent in the conditional that I'm analyzing. So that becomes my compound statement. P implies Q, and Q implies R. Altogether, this implies P implies R. Okay, so several columns. We know we're going to have 8 rows in total. So I had to make sure and leave myself enough space to put all this down. Looks like we did it though. All right. So remember, when you have 3 component statements, 8 rows is what we end up with. True, 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 false, true, false, true, false, true, true. So those are all, that's the first 4. And then let's see if I have true, false, false. That's one possibility. False, true, false, 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 true. And then finally all falses. Okay, that's all possible combinations, and you should be able to see that I have 8 rows. Next up, we're looking at P implies Q. First column implies the second. So I have true implies true, true implies true for my first two. That's true, and that's true. True implies false gives me false. False as my antecedent automatically, let me be a little more neat here. False automatically gives me a true conditional. True implies false will be false. And then the last 3 have false antecedents. All of those will be true. Okay? Next up, I have Q implies R. Second column implies third column. True implies true. That gives me true. True implies false. Gives me false. False implies true. Well, false antecedent means a true conditional. True implies true. That's true. False antecedent here, here, and here. All of those will be true. So I kind of jumped past this one, and then notice true implies false gives me false. Okay? Much more involved in the previous examples just because of the size of this truth table, but we're getting through it. Next up, I have the 2 previous conditionals, P implies Q and Q implies R, and a conjunction. So remember, we're looking for where we have a true in both cases to give us trues. That happens in the first row, does not happen in the second or third row. I have true, true in the fourth row, not in the fifth. I have a false in there, so that makes this false. True, false, that's going to give me a false consequent, and then notice true, true, and true, true. So my, I think I said consequent before, conjunction. So I'd have true in both of those cases. All right, now we're almost there. This, in the square brackets, is the previous column. That's my antecedent, and I want that to imply P implies R. I just realized that I left off P implies R. Shoot, forgot a column. Okay, let's see if I can squeeze that in somewhere. I didn't really leave myself a ton of space. We're going to be a little sloppy here, but I think I can make this work. So one thing that we needed was P implies R. See, with these big arguments, it can be kind of easy to miss important columns. Okay, so I'm going to make this last guy here. P implies Q, and Q implies R, all together implies P implies R. Now, if you make this mistake, it's very easy to make, forgetting a column in a truth table. Hopefully you'll be using pencil, so you can not have to scribble it out like I did. But that's okay. We'll make this work. P implies R. So that's column 1 implies column 3. True implies true. That's true. True implies false. That's false. True implies true. That's true. False antecedent means a true conditional, so that's going to be true. True implies false. That's going to be false. Notice the last 3 cases, 1, 2, 3, I have false antecedents, so those will all be true. Okay, now we can do this compound statement. So I have my antecedent in this column, my consequent in this column, and we're making a conditional. True implies true is true. The next 2 antecedents have a false truth value, making both of those true. I have true implies true, which is true. False implies, well, again, false as my antecedent in these next 2 entries gives me automatically true here. Finally, true implies true, true implies true. I have a tautology, truth everywhere. So that means that this is a valid argument. It was a much more complicated one to analyze, but we did it, and we ended up with a tautology. So finally, let's give a name for this form. Symbolically, we were looking at an argument of the form P implies Q for premise 1, Q implies R for premise 2. The conclusion was P implies R. This is called an argument, this argument is called reasoning by transitivity. If you've taken geometry, you might remember something called the transitive property that you did in those 2 column proofs that you would have learned in geometry. It's the same general concept here, the same use of that term transitive or transitivity. Arguments of this type are always valid. Okay, that is going to wrap things up for us in chapter 3.